Okay, so continuing our look at equilibrium. So we talked about equilibrium and how once a reaction is in equilibrium, it means that the forward rate of reaction is equal to the reverse rate of reaction, right? And we know that it has to occur within a closed system. Ideally, of course, it is a must-have if you're dealing with gases. So it's important to know that when we're talking about equilibrium, right, we're not discussing those reactions that are less than 1% complete or more than 99% complete, right? So when we talk about equilibrium, we're discussing the ones that are between 1 and 99% completion, right? So you know that from the last lesson that even if we say a reaction has gone to completion, that does not mean you'll never have 100% product, right? Some amount of those products, even if it is less than 1%, will revert back into reactants once again. So once we have an established equilibrium between that 1 and 99%, there's a way that we're actually able to measure the quantities at equilibrium using what's called an equilibrium constant. Okay, so you're going to see a lot of different K's in this unit. So, KEQ, KA, KB, KW, KSP. There's going to be a bunch of K's, okay? So K is always the same. So what I mean by that is it's always an equilibrium constant, okay? Now, they can have the little subscript be different depending on what type of equilibrium we are looking at. So for just as an example, when we start looking at acid-base reactions, you're going to start having the equilibrium constant for an acid reaction or the equilibrium constant for a base reaction. Okay, but in general, when we're not being specific about what type of reaction we're looking at, it's just simply KEQ, which means the K or equilibrium constant for any equilibrium. Okay, so today's goal is really learning about how to set up this K expression. And the K expression is going to be used, like I said, over and over again throughout the course of this unit. So learning at the beginning how to set up a K expression properly is going to make your life easier when we look at other types of Ks later on, because they all work in exactly the same way. Okay, so equilibrium constant. So first of all, the K that we're looking at here has nothing to do with the rate law expression K. So if you remember, we had R is equal to K, and then we have our reactants to our exponents. This was from our last unit for kinetics. This K, the rate law expression K, has nothing to do with this K. Okay, so I kind of want you to get that out of your head. So don't think of that as being equilibrium. So how to set up an expression for K for equilibrium constants is always the same. So the setup is products over reactants. Okay, so products over reactants. So another thing to keep in mind is the only things that can go into this expression are concentration values. So meaning, and it says this here as well, so meaning if you have a solid or a pure liquid, those cannot go into this K expression because we're dealing with equilibrium concentrations. So if you have a pure substance, there's no concentration for a pure substance because it's not a solute in a solvent, right? So typically you're looking for gaseous and aqueous components to go into this expression. Okay, so let's imagine for a second, here's our reaction. So the lowercase letters are representing the coefficients, and the uppercase letters are representing our compounds. So imagine for this example that all of these substances are aqueous. Okay, so meaning they're all going to go into this expression. So you put the product concentrations on top and the reactant concentrations in the denominator on the bottom. And what we do is we multiply them. So it's a concentration of C times the concentration of D, right? So let's imagine, right, it's like there's an X there. The concentration of A times the concentration of B. Now, we do have exponents in this case, okay? But these exponents are, again, have nothing to do with the rate law exponents that you were used to doing in the last unit. The exponents that are part of the K expression is actually the coefficients in this case. So you'll notice here we have the concentration of C to the exponent of the lowercase c. So meaning whatever this exponent was would go, whatever the coefficient was would belong to the exponent for that substance. The coefficient in front of D is now the exponent for D, etc., etc. Right? So lower cases are the coefficients, upper cases are the compounds. Note, not pure substances. They would have to be concentrations. Only concentrations at equilibrium go into this expression. So the K is a constant known as equilibrium constant, and it can be written for any system that reaches equilibrium. Okay, so that's what I mean by it has to be that 1 to 99%. If it technically does not have an established equilibrium, you cannot create a K value or a K expression. Okay, now the concentrations that are plugged into this number here, to this K, have to be at equilibrium. Okay, so they must be at equilibrium, and it is for a particular temperature. So what I mean by that is, let's say for a reaction at 25 degrees Celsius, the K value is 10. Okay, but maybe at 50 degrees Celsius, the K value is, 27. The K value will change depending with the conditions that the reaction is happening under. So let's just take a look at, before we get into that one, we'll do a different example. So let's say you had 2A solid plus B AQ, and we have an equilibrium with 3C gas. Okay, and let's say I want to make a K expression for this. So the K would be C to the exponent 3 over, so the A would not be included because it is a solid, so it would simply be over B, and of course it's the exponent 1 because there is no coefficient there. Okay, so notice A is not included. Let's look at something else. So what if we had only, we had one reactant only, and it was, let's say something like this. Okay, so setting up a K for this, you would have B to the exponent 2, C to the exponent 3, and it would be over, technically over 1 or over nothing because A is not included here. So when you're writing out the expression, it would simply just be this here. So K is equal to the concentration of B squared the concentration of C to the 3. And this is, of course, being multiplied. Vice versa, what if we had only a solid product or a liquid product, right? Let's say something like this. Oop, I should have had that. Let's say C liquid, right? My K expression would be nothing on top because my products go in the numerator and my product is not a concentration value. So it would be 1 over, and let's make that a gas, 1 over A times B squared. Okay, so the K expression setup only involves gases and aqueous substances. So even if you have one side of the reaction that has nothing to write in, it's like you're putting in the number 1. Okay, so looking at this one with a real example, here we have HI becoming H2 and I2. So here's our K expression, right? So our K expression is the concentration of hydrogen times the concentration of iodine. The coefficients are 1, so it's like to the exponent 1, over the concentration of HI squared, right? Everything is a gas. They are all included in this expression, right? So concentration, it doesn't matter if you're dealing with a gas or a solution. So it doesn't matter if it's a gas or if it's AQ. you're dealing with the same unit. So it's always moles per liter. Okay, so you're probably wondering, well, what would the unit of K be then, right? So K technically is dependent on the units that are involved over here, right? So this is moles per liter times moles per liter over moles squared per liter squared. So the unit of K changes every single time with every reaction because it's going to be different, okay? So it's a little bit different from our last unit. The last unit, I did want you to work out the units for K. Okay, when we're dealing with equilibrium K values, we are going to be reporting the value without units. Okay, so does that mean that K does not have its unit list? No, that's not true. Okay, it's just that typically we report K with no units, and you'll notice your textbook and other sources, if you're reading about equilibrium constants, very rarely do they include units here. It's just kind of assumed the units will have to match up with whatever the expression happens to be. Okay, so equilibrium law. So the law of equilibrium essentially explains the process of achieving our K expression. So this paragraph here that we'll look at together is essentially describing what this setup is. So it says, in a closed system at equilibrium at a fixed temperature, so meaning it's got to be at equilibrium and it has to be at a specific temperature, the product of the equilibrium concentrations divided by the equilibrium concentrations of the reactants, where they are raised to the power equal to the coefficient of the substance in a balanced equation. So yeah, in a nutshell, it's products over reactants. You multiply the concentrations, the exponent is the coefficients. What you end up getting is a constant ratio for that particular temperature with that equilibrium. So what does K tell us? What kind of information does K give us? Okay, so the key there is it's products over reactants, right? So it's always product concentration over reactant concentration. So actually, the relative value of what K is tells us a lot about the type of reaction we are looking at. So think of any time you're dealing with fractions. If you have a large numerator and a small denominator, when you divide those two out, your K value is going to be large, right? So let's say I had, I'm just going to make up numbers here, right? 500 divided by 2, I'm going to get the number 250, right? Whereas if I have a small number divided by a large number, I'm going to get a very small answer here. Right, so if we work that out, 2 divided by 500 is 0.004, okay? So essentially, if you have a large numerator, you're going to have a relatively large K. If you have a large denominator, you're going to have a relatively small K. Well, that in essence will tell you, okay, do I have more product or do I have more reactant in this equilibrium? If you have a relatively large K value, right, like in this example, that means you have way more product than you have reactant. The numerator concentrations are giving us a larger value than the denominator concentrations. And vice versa. If your K value is small, that means you have way more reactant than you have product. So meaning your equilibrium is going to have more in the reverse reaction than it would in the forward. Of course, if your K value is close to the number 1, so let's say we have K is 501 divided by 499, right? Let's work that out. Right, so we have 1.004. Okay, it's close to 1. That tells us you have equal values of reactants and products, right? So the concentrations are relatively the same.